The mountain does not announce itself. It simply exists. Massive, indifferent, older than any name humanity has pressed upon it. From a distance, in the thin gray light of an Appalachian morning, it resembles every other ridge in the chain, a dark shoulder of sedimentary rock draped in second-growth timber, folded into the earth 400 million years before the first man arrived to break it apart. But this mountain is hollow now. Somewhere beneath 1,200 feet of shale and limestone and sandstone compressed into geological time, a machine is still running. Not metaphorically, not in memory. The percussion of its operation, a low, rhythmic concussion felt more through the soles of boots than through the air, has not ceased since 1959. The coal company sealed the surface entries, padlocked the ventilation shafts, and filed its abandonment paperwork in triplicate with the Commonwealth of Pennsylvania. The lawyers drove away. The superintendents drove away. The men, those who were left, drove away. The machine did not leave. Inside those sealed chambers, in passages too narrow for a standing man, in galleries carved at angles that suggest geometry born of desperation rather than engineering, a continuous miner stands frozen in the darkness. Its tungsten carbide cutting drum, 11 feet wide, studded with 48 steel bits weighing 3 pounds each, rests against a coal face that has not moved in 60 years. Methane seeps through fractures in the roof strata and pools in the low corners. Sulfuric acid drains through abandoned sump lines into the water table beneath 3 counties. The machine ate and ate. And when the men who fed it were finally consumed, by economics, by legislation, by the slow collapse of a world built entirely on combustion, it was left precisely where it stood. This is not a story about coal. It is a story about appetite. Industrial appetite. The particular American hunger that mistakes perpetual extraction for progress, that confuses the depth of a mine with the measure of civilization. It is a story about what happens when a nation builds its entire thermal architecture upon a single, irreplaceable, exhaustible resource, and then builds a machine so large, so specific, so singular in its purpose, that the machine itself becomes the argument for continuing, even when continuing means the mountain must be consumed entirely. Even when continuing means the men inside it cannot come out. The Earth Eater did not discriminate. It consumed coal. It consumed mountain. It consumed men's lungs, men's hearing, men's futures, men's sons. And when it was abandoned, it left something behind. Something that continues to burn, to drain, to subside, to poison. In the same darkness where it was born. There is a particular category of industrial object that transcends its function and becomes something else entirely. Something closer to ideology made mechanical. The steam hammer. The blast furnace. The cotton gin. Objects so precisely calibrated to the extraction of value from raw material that their existence reshapes not only the landscape they operate within, but the social order of everyone who lives within their gravitational pull. The continuous miner belongs to this category. Introduced to American underground coal operations in the late 1940s, the continuous miner was the most significant leap in underground extraction technology since the invention of the longwall system in 17th century Britain. It was, by any reasonable engineering metric, a masterwork. A rotating cutting drum, hydraulically pressured against the coal seam, capable of removing 8 to 14 tons of coal per minute from a working face. More coal than a hand loader could produce in 2 full shifts. It required no drilling. It required no blasting powder. it required no waiting. It simply advanced, and the coal fell. The paradox is this. The machine designed to save lives by removing men from the most dangerous work in the mine, the cutting face, where roof falls and methane ignitions killed thousands annually, ultimately concentrated those same men into smaller, tighter, more dangerous configurations around itself. It reduced the workforce required at the cutting face while simultaneously increasing the production rate so dramatically that entire seams once considered marginally economic became viable. Which meant deeper mines, which meant more methane, which meant more roof instability, which meant more men in more mountains, in more danger, at more depth. The question the continuous miner poses is not technological. It is moral, and it is precise. When a tool increases both productivity and lethality simultaneously, when it makes a process both more efficient and more dangerous by virtue of the same mechanism, who bears the cost? The corporation that purchased the machine, depreciated it over 7 years, and walked away from the mountain when the seam ran thin? The state that issued extraction permits in exchange for royalties and employment statistics? The federal government that defined safety standards 3 decades after the machine was already in operation? Or the men, and always in this industry they were men, who operated it in the dark? History does not answer this question cleanly. History only records what happened next. What happened next was this. Between 1950 and 1970, the continuous miner transformed American coal production beyond recognition. Output per man-hour tripled. Employment in underground mining fell by 60%. 42,000 miners lost their livelihoods in Appalachia alone within 15 years of the machine's widespread adoption. And the mountains, the specific mountains where the most powerful continuous miners operated, began to change in ways that were not immediately visible, but that would not remain invisible forever. The machine ate the mountain, and the mountain, in ways that took decades to fully manifest, began to eat back. The year is 1947. The United States has just emerged from the most total war in human history, and the economy, temporarily disoriented by the cessation of military production, is reorganizing itself around a single urgent question: how to feed the furnaces of American industry. Consumed coal in quantities that are now almost inconceivable. A single integrated steel mill in Pittsburgh or Gary or Bethlehem required between 3,000 and 8,000 tons of metallurgical coal per day to sustain continuous operations. The electrical generation capacity being constructed across the eastern seaboard, dam projects, thermal plants, municipal systems being electrified for the first time, demanded bituminous coal by the trainload, every day, without interruption. The railroads themselves burned coal. The schools burned coal. The hospitals burned coal. In the winter of 1946, when John L. Lewis called his United Mine Workers to strike for the second time in 12 months, President Harry Truman briefly nationalized the mines under the War Labor Disputes Act and ordered miners back to work by executive order. Because the alternative, a coal stoppage lasting more than 3 weeks, threatened not labor relations, but national function. This was the context in which the continuous miner arrived. Not merely as a piece of equipment, but as a solution to a political crisis as much as an engineering one. The labor movement in underground coal was the most powerful, most militant, most historically consequential in American history. The UMW under Lewis had shut down the nation's industrial base twice in 2 years. Management and government alike understood that the long-term answer to labor power in the mines was not negotiation. It was mechanization. Remove the men from the cutting face, and you remove the leverage. You cannot strike a machine. The Joy Manufacturing Company of Franklin, Pennsylvania, already the dominant manufacturer of underground mining equipment, had been developing continuous mining technology since the early 1940s. Their engineers, working from preliminary concepts developed in Germany and adapted to the specific geological conditions of Appalachian bituminous seams, produced the first commercially viable continuous miner in 1948. The Joy 2CM, a machine weighing 42 tons, measuring 22 feet in length, consuming 250 kilowatts of electrical power, and capable of cutting a 13-foot wide, 5-foot high entry through soft bituminous coal at a rate of 12 feet per minute, entered production at the Culver Mine in Clearfield County, Pennsylvania, on March 14, 1949. The mine superintendent's log entry for that day occupies 3 lines. Continuous miner installed and operational. Production for shift, 847 tons. Previous record for shift production by conventional methods, 204 tons. 4 times the output, the same number of men. The implications were understood immediately by everyone who read that log entry. The implications were catastrophic for everyone who did not. The Joy 2CM was not a beautiful machine. It made no concessions to aesthetics. It was a brutalist object, low-slung, massively constructed, designed to exist in a space where men crawled and ceiling rock pressed down with the weight of a mountain. And it looked precisely like what it was. A tool built for one purpose, without apology, without ornament, without any quality that was not in direct service of that purpose. Its cutting drum, the forward element that gave the machine its distinctive silhouette, rotating at between 40 and 60 revolutions per minute against the coal face, was the engineering heart of the system. The drum itself was a cylinder of forged steel, 11 feet in diameter in the largest production models, studded in a helical pattern with replaceable cutting bits made from tungsten carbide-tipped steel. Tungsten carbide, the densest commercially workable material available to industrial manufacturing at mid-century, could sustain cutting pressures and temperatures that destroyed conventional steel bits within hours. A full set of cutting bits on a continuous miner drum, 48 to 64 bits depending on the model, cost in 1953 dollars, approximately $1,200. A full set lasted, under normal operating conditions in a medium-hardness bituminous seam, approximately 1 shift. The economics of this were extraordinary. $1,200 per shift for consumable bits against an output value, at 1953 prices, of between $8,000 and $14,000 per shift of coal extracted. The machine paid for its own bits out of production revenue in the first 40 minutes of every operating shift. The companies understood this arithmetic perfectly. Between 1949 and 1965, Joy Manufacturing sold 1,847 continuous miners to American coal companies. Competing manufacturers, Jeffrey Manufacturing, Lee Norse, Goodman Equipment, entered the market and collectively sold an additional 2,000-plus units. By 1960, continuous miners were operating in 78% of the major underground coal operations in Appalachia, the Illinois Basin, and the western coal fields. Each machine displaced, on average, between 12 and 18 hand loaders from the cutting section. The math was irreversible. In 1950, the United States employed 416,000 underground coal miners. In 1960, that number was 169,000. In 1970, it was 128,000. The machines had not reduced coal production. Production had increased by 30% over the same period. The machines had simply made the men unnecessary. Not all of the men, never quite all of them, But entire communities built around the expectation of mine employment found themselves holding on to an industry that was mechanically discarding them. The machine rose. The communities that had fed the machine their sons for 3 generations watched the employment numbers fall and tried to understand what they were witnessing. They had been told that mechanization meant progress. They had not been told what progress looked like from the outside of the mine gate. In Harlan County, Kentucky. In McDowell County, West Virginia. In Clearfield and Cambria and Indiana counties in Pennsylvania. The same story unfolding in the same coal-gray light. The machine ate, and the men watched from outside. To understand what the continuous miner did to a mountain, it is necessary to understand what a mountain is. Appalachian bituminous coal seams, the Pittsburgh seam, the Sewickley, the Freeport, the various upper and lower Kittanning seams that provided the majority of Eastern American coking coal, were not simply layers of compressed carbon. They were load-bearing structural elements within a complex system of interbedded sedimentary rock. The coal seam, typically 3 to 7 feet thick in productive sections, was overlain by immediate roof rock, usually shale, occasionally limestone, sometimes the particularly treacherous black shale, locally called draw rock by miners who understood its behavior, which was in turn overlain by main roof strata extending upward through hundreds of feet of alternating hard and soft rock to the surface. This system was in equilibrium. It had been in equilibrium for a very long time. The equilibrium depended on the coal remaining in place. The coal, compressed by the weight of the overburden above it, transmitted vertical load to the floor rock below and maintained the structural integrity of the roof above. When miners removed coal, they necessarily disturbed this equilibrium. The conventional answer to this disturbance, developed over centuries of underground mining practice, was the pillar system. Leave sufficient coal in place in dimensions calculated against the depth of cover to support the roof. The removed coal is profit. The remaining coal is architecture. The continuous miner complicated this calculation in ways that were not fully understood in 1949. Because the continuous miner could cut a working entry at 12 feet per minute, and because it could cut that entry to widths of 13 or 14 feet, significantly wider than conventional drill and blast methods typically produced, it altered the stress distribution in the surrounding rock mass more rapidly and across a larger area than any previous mining method. The roof rock above a freshly cut continuous miner entry did not have time to adjust gradually to the new stress state. It was subjected to what engineers would later term dynamic stress redistribution, a sudden, large-scale transfer of load to the remaining coal pillars adjacent to the entry. In soft coal seams with competent limestone roof, this was manageable. The pillars were stiff. The roof was strong. The redistribution occurred, the system found a new equilibrium, and mining continued. In seams with shale immediate roof, which described the majority of productive Appalachian bituminous operations, the situation was different. Shale is a laminated rock. It fails in layers, parallel to its bedding planes, under tensile stress. When the coal beneath it is rapidly removed over a wide area, the lower layers of shale experience tensile failure almost immediately. They separate from the layers above. They sag. They fall. The men who operated continuous miners in the 1950s and 1960s called this process by a name that captured its character with industrial precision. They called it waiting. The roof was waiting. The mountain was pushing down. A skilled roof bolter, the man responsible for installing the steel expansion bolts that secured the shale to the more stable rock above, could work at a pace roughly equivalent to the continuous miner's advance if conditions were ideal. Conditions were never ideal. The continuous miner was always ahead of the roof bolter. The distance between the last installed roof bolt and the active cutting face, a distance called the unsupported span, was the most dangerous geography in the mine. In a slow-cut conventional section, the unsupported span was typically 4 to 6 feet. In a continuous miner section advancing at full production rate, the unsupported span could reach 12, 15, 20 feet before bolts were installed. The engineers who designed production schedules understood this. They understood it as a trade-off, a calculated risk against the production value of maintaining machine advance rate. They expressed this understanding in terms of acceptable risk parameters and statistical probability of roof fall events per 100 machine shifts. The miners understood it differently. They understood it as the space between the last bolt and the cutting drum, measured not in feet, but in heartbeats.
There was a flaw in the machine that nobody wanted to find, because finding it would have required slowing the machine down. The continuous miner generated coal dust. This was not a secret. It was not a surprise. Any method of mechanically disrupting a coal seam, drilling, blasting, cutting, liberates coal dust. The cutting drum of a continuous miner, rotating at 50 revolutions per minute against a bituminous coal face, generated coal dust in concentrations that exceeded anything previously encountered in underground mining. A conventional drill and blast section produced, during the cutting phase, dust concentrations of 2 to 4 milligrams per cubic meter of air. A continuous miner in full production produced dust concentrations of 12 to 30 milligrams per cubic meter. This distinction was medically decisive. Coal dust, inhaled in sufficient concentration over sufficient time, produces coal workers' pneumoconiosis, black lung disease. The disease is progressive and irreversible. The dust particles, fine enough to penetrate to the alveolar tissue of the deep lung, lodge in the pulmonary parenchyma and provoke an inflammatory response that, over years and decades, replaces functional lung tissue with fibrous scar tissue. A miner with advanced coal workers' pneumoconiosis cannot breathe when walking. He cannot breathe when sitting. He dies breathing. The act of breathing itself becomes, in the final stages, an exhausting labor that the damaged lungs are no longer capable of sustaining. The American coal industry was aware of the dust problem by 1952. Internal documents, some of which did not reach public scrutiny until congressional investigations in 1969, demonstrate that dust sampling programs conducted by major operators in the early 1950s had identified dangerous concentration levels in continuous miner sections. The documents are remarkable for their clarity. They describe the problem with precision. They do not describe a solution. What they describe, in the language of industrial management, is a strategic decision to manage the information rather than manage the dust. Dust sampling results were not shared with miners. They were not shared with the Federal Bureau of Mines. They were not shared with insurance actuaries calculating occupational disease liability. They were filed in internal archives, where they remained for 20 years, accumulating behind the corporate confidentiality that the law of that era permitted and that the power differential between management and labor enforced. The machine also generated methane. The cutting action of the rotating drum against the coal seam, the same action that made the machine so productively miraculous, disturbed the natural methane contained within the coal matrix at a rate proportional to the cutting speed. A conventional drill and blast section, which cut coal in discrete, time-separated operations, gave mine ventilation systems intervals in which to dilute and exhaust liberated methane between blasts. A continuous miner, cutting continuously, liberated methane continuously. The ventilation engineering required to maintain methane concentrations below the lower explosive limit, 1.25% by volume in air, in a continuous miner section was significantly more demanding than in conventional sections. The federal regulations governing methane concentration limits had been written in 1941 for conventional mining. They were not updated to account for continuous miner conditions until 1969. For 20 years, continuous miners operated under methane safety regulations designed for a different method, at different production rates, in different ventilation geometries. The hidden flaw was not a design defect in the machine. The machine worked exactly as designed. The hidden flaw was the gap between what the machine did and what the regulatory environment assumed it did. That gap was 20 years wide. In those 20 years, the methane accumulated, the dust accumulated, the scarred lungs accumulated, and the profits accumulated alongside all of them, in precisely the same darkness. Shift change at a continuous miner section happens at 7 a.m., 3 p.m., and 11 p.m. The incoming crew assembles at the lamp house 45 minutes before shift start. There are between 8 and 12 men, depending on the section configuration. The continuous miner operator, his helper, 2 or 3 roof bolters and their helpers, shuttle car operators, a Brattis man responsible for ventilation curtains, and a section foreman who carries both a methane detector and the authority to send men home without pay if, in his judgment, conditions do not permit safe entry. The lamp house issues each man a cap lamp with a fully charged battery pack, a self-rescuer, a small personal oxygen device intended to sustain breathing for 1 hour in an irrespirable atmosphere, and a brass check tag stamped with his employee number. The check tag goes on the board. When a man comes out of the mine, his tag comes off the board. Any tag remaining on the board at the end of shift means a man is underground. This system, unchanged since the 19th century, is the mine's primary accounting of human beings. The men ride the man trip, a low, open rail car pulled by a battery locomotive from the surface drift entry to the section. In a deep mine, this journey takes 20 minutes. The ride passes through the main entries, which are high and relatively wide, then through the sub-mains, which are lower and tighter, and finally into the section entries, which are as small as the seam height allows. In a 5-foot Pittsburgh seam section, a man of average height must keep his head bent for the entire shift. Over 30 years of mining, this posture becomes habitual, permanent, and eventually pathological. The noise of the continuous miner in full operation can be heard before the section is reached. It penetrates the rock itself. It is not a sound, exactly. It is a vibration experienced through the seat of the man trip, through the floor of the mine, through the soles of the rubber boots. When the crew enters the active section, the vibration becomes a sound, and the sound is enormous. A bass register mechanical roar, overlaid with the high-frequency screaming of tungsten carbide against coal, punctuated by the hydraulic groan of the gathering arms that sweep the cut coal toward the machine's conveyor chain. The coal dust in the air of a working continuous miner section is not visible as individual particles. It manifests as a general reduction in visibility. A man standing at the continuous miner operator's position, 15 feet from the cutting face, can see the operator and the cutting drum and the coal face beyond it. But the far wall of the entry is obscured. A cap lamp in this atmosphere projects a cone of light approximately 8 feet before the beam is scattered into diffuse gray luminescence. This is the visual world of the continuous miner section. Gray light, gray dust, gray coal walls, gray shale roof pressing down from above. A man named Raymond Hostetler, who operated a continuous miner at the Helen Mine in Cambria County, Pennsylvania, from 1956 to 1974, described the sensory experience of his workplace in testimony before the Pennsylvania Coal Commission in 1971. He said, "You get so you don't think about the mountain above you. If you thought about it, you couldn't work. You think about the machine. You think about the cut. You watch the roof, and you watch the face, and you watch the drum. And when the shift ends, you ride out, and the sun is something you weren't expecting." He said it mildly, as a man states a fact about weather. He said it with the flat affect of someone who has processed a thing so many times that the processing has removed all excess emotion, leaving only the shape of the experience, the outline of it, the fossil impression. He was 53 years old when he gave that testimony. His lung capacity, measured by spirometry that same year, was 41% of predicted normal. He had been diagnosed with Category 2 progressive massive fibrosis. He had not been told, when he went underground for the first time in 1956, that the dust concentrations in continuous miner sections had been measured and recorded and found dangerous 6 years before he first breathed them. He died in 1979. He was 61 years old. His cause of death was listed as respiratory failure. His brass check tag is still in his daughter's possession. She keeps it in a kitchen drawer in Nantyglo, Pennsylvania, beside a photograph of her father taken at a company picnic in 1961, in which he stands in full sunlight, squinting slightly, wearing a white shirt he had ironed himself, looking like a man who expects the future to resemble the present.
November 20th, 1968. Farmington, West Virginia. Console number 9 mine. The explosion begins at 5:30 a.m., before the day shift is fully descended. 78 men are underground. The initial blast, triggered by a methane ignition in one of the continuous miner sections operating in the deeper workings, detonates with a force sufficient to blow the surface ventilation fans off their mounts. A second explosion, more powerful, follows 23 seconds later. Then a third. The surface structure above the main shaft entry collapses. The ventilation system, the primary mechanism for diluting methane to safe concentrations, ceases to function. Rescue teams cannot enter. The methane-laden atmosphere inside the sealed mountain will ignite if oxygen is introduced. The rescue teams wait. The families wait. The company issues statements. The government issues statements. The miners' families stand at the mine mouth in November cold for 9 days. And on the 9th day, the mine is sealed, entombing 78 men, 19 of whom were never reached, never recovered, and whose remains exist still within the sealed rock beneath Marion County. The explosion at Farmington No. 9 was not the worst disaster in American coal mining history. The Monongah disaster of 1907, which killed 362 men, holds that distinction. The Centralia No. 5 explosion of 1947 killed 111. But Farmington occurred in the age of television, and the 9 days of waiting, the families at the mine mouth, the rescue teams and their equipment, the government officials in their overcoats, was witnessed in living rooms across the country in a way that no previous coal disaster had been. It also occurred at the precise historical moment when the United Mine Workers of America, under the increasingly autocratic leadership of Tony Boyle, was losing its institutional credibility as a defender of miner health and safety. The UMW had been aware of the dust problem for years. The union had known about the dust sampling data suppressed by major operators. The union had chosen, under Boyle's leadership, to prioritize wage negotiations over health and safety demands, in part because Boyle understood that a healthy workforce was a workforce with leverage, while a sick workforce was a workforce that could not strike effectively. The surviving miners at Farmington and at 100 other continuous miner sections across Appalachia, where the dust concentrations had been building in men's lungs for 15 years, did not wait for the union. They organized themselves. In the autumn of 1968, before Farmington, a physician named Isidore Buff and two colleagues, Howie Wells Jr. and Donald Rasmussen, had begun conducting pulmonary function tests on Appalachian miners, independent of any company or government program. Their results were devastating. 65% of working miners tested in Mingo County, West Virginia, showed measurable pulmonary impairment. 30% showed advanced fibrosis. After Farmington, these numbers became a political document. The Black Lung Association, formed by miners themselves, without institutional support, operating from church halls and union locals where the established leadership was absent or hostile, organized a wildcat strike in early 1969 that eventually involved 40,000 West Virginia miners. They were not striking for wages. They were not striking for hours. They were striking for recognition of a disease that the industry had spent 20 years pretending did not exist at the rates at which it existed. The West Virginia legislature, under extraordinary pressure, passed the Black Lung Benefits Act in February 1969. Congress followed with the Federal Coal Mine Health and Safety Act of 1969, the most comprehensive coal mine safety legislation in American history. The act established mandatory dust sampling, mandatory dust concentration limits, mandatory methane monitoring requirements, and, for the first time, an enforceable federal inspection regime with penalty authority. It had taken exactly 20 years. 20 years from the first internal dust sampling data to federal law. 20 years of continuous miners cutting continuous entries while the dust accumulated in continuous lungs. The machine had not changed. The men who operated it had changed everything. The Federal Coal Mine Health and Safety Act of 1969 did not stop the continuous miner. Nothing stopped the continuous miner. It continued to operate in American coal mines through the 1970s, the 1980s, the 1990s, in progressively more sophisticated versions. The Joy 10cm, the Joy 12cm, the Joy 14cm, each generation cutting wider entries, consuming more power, advancing faster, generating more dust. Dust suppression systems, water sprays, ventilation curtains, scrubber units were added, mandated, improved. Dust concentrations in working sections dropped significantly between 1970 and 1990. The machine became, by regulatory compulsion, somewhat safer. Somewhat. The compensation system established for black lung claims became, in the decades after 1969, a case study in institutional resistance to acknowledged obligation. The Black Lung Disability Trust Fund, financed by a per-ton excise tax on coal production, was perpetually underfunded, perpetually contested, perpetually administered in ways that maximized the number of denied claims. Between 1970 and 2010, approximately 78,000 coal miners or their surviving dependents received black lung benefits. This number represents a fraction of the actual disease burden. The Social Security Administration and the Department of Labor, the two agencies sharing administrative responsibility for the program, processed claims through a review system that required claimants, many of whom were already incapacitated by their disease, to navigate a legal and medical bureaucracy that denied initial claims at rates exceeding 70% for most of the program's history. A miner who filed an initial claim could expect, on average, to wait 4 to 8 years for final adjudication. Many died waiting. The economic consequences for Appalachian coal communities were equally systemic and equally protracted. The mechanization wave that the continuous miner initiated, and that longwall mining systems, introduced at scale in the 1970s, dramatically accelerated, eliminated underground mining employment with a thoroughness and finality that no subsequent economic policy has meaningfully addressed. McDowell County, West Virginia, which employed 28,000 underground miners in 1950, employed fewer than 1,800 in 2000. The county's population fell from 98,000 to 27,000 over the same period. Per capita income, relative to the national median, declined every decade from 1960 forward. The infrastructure of a coal company town, the company houses, the company store, the company hospital, the company school, all of it built on the assumption of continuous mine employment, was not designed for an economy that no longer needed the labor it had been built to house. When the mines closed, or mechanized to a fraction of former employment levels, the infrastructure did not adapt. It collapsed. It was abandoned. The houses rotted. The stores closed. The hospitals became urgent care facilities with inadequate funding, then became clinics, then closed. The continuous miner also left a physical legacy in the mountains it had consumed. Abandoned mine drainage, the sulfuric acid formed when mine water contacts pyrite-bearing strata exposed by mining, has contaminated more than 5,500 miles of Appalachian streams. The orange-red stain of acid mine drainage in a mountain stream is one of the most visually distinctive signatures of the coal era, and one of the most persistent. Some drainage sites in Pennsylvania and West Virginia have been actively flowing for 60 years and are projected by hydrological models to continue flowing for another 2 to 3 centuries. The mines that were sealed, the ones where the machine was left underground, where the mountain was sealed with a poured concrete plug over the drift entry and a chain-link fence around the surface subsidence zone, did not become inert. They became slow catastrophes. Methane continued to accumulate in the sealed workings and continued, in some cases, to ignite. Centralia, Pennsylvania, where an underground mine fire has burned since 1962, is the most visible example of this phenomenon, but it is not unique. The Pennsylvania Department of Environmental Protection tracks 45 active underground mine fires in the state. Additional fires are suspected in sealed workings that have not been penetrated since closure. The mountain does not simply accept what has been taken from it and become still. It adjusts. It redistributes. It continues, in geological time, to process the violence done to its interior. There is a ridge in Clearfield County, Pennsylvania, where the surface subsidence from abandoned continuous miner workings has created a topographic anomaly visible from the county road below. The ridge, which should present a smooth, forested slope, shows instead a series of irregular depressions, 10, 12, 15 feet deep in some places, 50 to 80 feet in diameter, that give the hillside the appearance of a landscape that has been struck repeatedly from within. Which is, in the most literal sense, what has happened. The depressions form where the coal pillars that remained after mining, the pillars calculated against depth of cover and seam height and roof rock competency by engineers who did their best arithmetic in 1953, have finally yielded to the weight of the mountain above them. The pillars compress slowly. Then they fail suddenly. The surface sinks. The depression forms. The trees growing in the depression lean at angles that suggest a world subtly, irrevocably tilted. No one owns these depressions officially. The coal company that created them was absorbed by a larger company in 1961, which was absorbed by a larger company in 1978, which declared bankruptcy in 1992, which discharged its environmental liabilities in that proceeding, which means the liabilities pass to the state, and the state passed them to a remediation fund that has been underfunded for 30 consecutive years. The machine that created these depressions, the specific continuous miner that cut these specific entries in the specific winter of 1958, is still inside the mountain. Or what remains of it is. The steel has corroded in the acidic mine water. The rubber has dissolved. The tungsten carbide cutting bits have survived better than most of the machine because tungsten carbide does not corrode easily. And the bits may be there still, studding a collapsed cutting drum in a flooded entry under 1,200 feet of rock, harder than the coal they were made to cut, outlasting by centuries the men who installed them and the company that owned them and the economy that required them. The legacy of the continuous miner is not simple, and any account that makes it simple is dishonest. The machine produced coal that heated American homes and powered American industry during the decades when the American economy was the dominant engine of global production. It produced coal for steel mills that built the bridges and buildings and machines that constitute the physical infrastructure of modern American life. The standard of living that coal-powered industrialization created, the reduction in mortality from cold, from disease, from physical deprivation, is real, and it belongs in the accounting. But the accounting must also include the men. The accounting must include the 78 men sealed inside Console Number 9 on November 20th, 1968. It must include the estimated 200,000 American coal miners who died of black lung disease between 1950 and 2000, a number derived from mortality studies rather than official records, because official records do not fully capture a disease that was officially denied for 20 years. It must include the 40,000 Appalachian mining jobs eliminated between 1949 and 1960 by mechanization, and the families those jobs sustained, and the communities those families populated. The accounting must include Raymond Hostetler's brass check tag in his daughter's kitchen drawer in Nanty Glo. It must include the orange streams. It must include the subsidence depressions in Clearfield County, where the mountain is still settling. The continuous miner operated on a principle of unlimited appetite. More coal, faster, deeper, wider. The machine itself did not choose this principle. The machine was incapable of choice. It was a cylinder of steel and tungsten carbide rotating in the dark, doing precisely what it was designed to do, consuming precisely what it was fed, stopping only when the coal ran out, or the economics ran out, or the men who operated it could no longer breathe. The question the machine poses, the question that the mountain poses, the streams pose, the check tags pose, is the question that every industrial civilization must eventually answer about the gap between what it can extract and what extraction costs. America has not fully answered this question. It has not fully answered it because answering it completely would require accounting for costs that cannot be easily monetized. The specific quality of air in a man's lungs, the specific color of water in a mountain stream, the specific weight of a check tag that never comes off the board. The machine is still inside the mountain. The entries are sealed. The company is gone. The men are mostly gone. The coal that remains in those sealed workings, in the unmined pillars, in the thin remnant seams, in the structural coal left to hold the roof that eventually failed anyway, will remain there until the mountain subsides around it, or the chemistry of groundwater dissolves it, across a time scale that makes human economies look momentary. The continuous miner cut its last entry in that mountain in 1959 and has not moved since. But the consequences of its cutting are in motion still. In the aquifers, in the subsidence zones, in the cells of the men who breathed its dust and whose children breathed the legacy of decisions made before they were born. There are things a machine can do that cannot be undone. There are things an industry can do to a landscape, to a workforce, to a civilization's relationship with the material world beneath its feet, that require not decades, but centuries to fully manifest. The mountain knows this. It has always known this. It is still settling. It is still, in its deep and geological patience, still in the slow process of reasserting itself against the violence done to its interior. This mountain that was hollowed, that was consumed, that was left sealed and dark and full of the evidence of appetite. The earth-eater ate, and the earth, in its own time, on its own terms, is eating back.